Good afternoon, everyone. Welcome. I'm Wei from the Machine Learning Platform team at Roblox, and joining me today are my awesome colleagues, Steve and Yiqing. Today, we are going to share how we leverage Ray to efficiently scale batch inference at Roblox. So here's what we will cover today. We will start with a brief introduction to Roblox and followed by an overview of our machine learning platform. Then we will deep dive into a few Ray use cases and then discuss the key components of our Ray job platform. So for those of you who aren't familiar with Roblox, Roblox is a platform that millions of people come every day to create, play, and connect with each other in all kinds of virtual experience created by our global community of creators. So AI have been deeply embedded in Roblox, especially when it comes to safety, which is essential to everything we do. So we leverage AI for real-time bot detection, voice and text moderation, and safety review of user-generated content in terms of like images, video, audio, 3D model, and even code. We will make sure everything is carefully reviewed before making them available on our platform. For creators, we introduce a bunch of very cool Gen AI features to speed up their creative process. I will demo a few in the following slides. For players, AI powers our recommendation and search systems, helping them to find the right experience, and when they click the play button, our matchmaking algorithm will help them to find the best available servers. So here is some examples that we released earlier this year. The first is the texture generator. So creators can simply use text prompt to quickly customize how a 3D object looks. So the texture will automatically conform to the shape of the 3D object, so it saves the creator tons of time and effort. Another one is avatar auto setup. So the creators can just simply upload a 3D model, and then this tool can help them to automatically create the avatar meshes and also the auto rigging, and then they can preview the animation, the skin tones, the clothing, and also preview the avatar bodies, everything right inside the Roblox studio. So this will help the avatar creation from hours to just minutes. Just in last month, we announced a new AI incubation project to develop a multimodal 3D foundation model for future generative creation. So to keep up with the rapid demand of ML, in the past few years, we developed a unified machine learning platform. This is built on top of many open source technologies. We use Qflow for its core ML components, such as pipelines and notebook servers, including Jupyter servers and VS Code servers. And we use Kserve with the NVIDIA Triton Inference server to support multiple ML frameworks running on CPU and GPU across our multiple data center and in the cloud. And on top of this, we developed a Roblox ML, a Python SDK, to make it super easy for our users to bring their prototype ideas all the way to production. So users can just run experiment in their notebook, and then they can launch it into a pipeline without needing to build the Docker images. And because our SDK will automatically help them to snapshot the runtime environment in the dev cluster. And when they need to make it to production, we have the CI/CD system for the pipeline and the model deployment. And user can simply use the GitHub comment to trigger the automatic load testing and the correctness testing. And with our model registry, user can use Roblox ML to upload and download models. And this will be automatically versioned to make sure the model artifacts are reproducible and traceable, which is very important for the production. And earlier this year, we also took one step further. We heavily invested in vLLM and directly contribute to vLLM open source project. And we built our ML gateway to efficiently support large models. But as AI and ML continues to evolve, especially with more and more Gen AI use cases and a huge unstructured data needs, we realize our existing solution cannot keep up with this rapid demand. So one area is batch inference. Traditionally, our users has been used Spark or leverage the online inference service or use pipeline to run their batch inference. So Spark, we all know that it's very good for structured data processing, but it's not so efficient for the ML tasks. And for real-time inference service, a lot of times you cannot fully utilize the compute resource and causing GPU starvation. And Steve will talk about this later in the use case deep dive. For pipeline loops, it requires our engineers to write their own logic to do data partitioning and also error handling, which is very time-consuming and also error-prone. So to overcome all these limitations, we turn to Ray. It can make it's super easy to efficiently scale batch inference workloads. And as you can see in this diagram, we integrate Ray with our existing ecosystem. And we also add the batch API to support large language model batch inference, which make it easier for users to run the LLM inference with optimal setups. And with Ray, we have seen optimal improve compute resource utilization and enable multi-stage processing in heterogeneous compute resources. And we also enable task parallelism with easier fault tolerance. And we have seen great efficient gain with Ray. So here is a few key results from our batch inference use cases. And since launching Ray, we have run Ray job daily. Next, let's have Steve to give some deep dive of our use cases.
Yeah, thank you, Wei. So I want to talk about some use cases of Ray data at Roblox that really justify this place in our ML platform. So first, we have Clip batch inference. So as you'll probably know, Clip is an OpenAI model that maps both images and text to the same embedding space. So we can tell how well a given text and image fit together. So we use this for semantic search for 3D assets, which helps developers to find 3D models in their inventory without needing to remember exactly what they're called. We use Ray data to backfill these embeddings. We also use Clip for clickbait detection. We have millions of experiences on Roblox, and inevitably some developers will try to copy logos from popular experiences and put them on their own thumbnails to bait users into clicking them. So to detect this, we're using YOLO to segment the logos from the thumbnails, and then we're comparing their clip embeddings against the embeddings of those protected logos. Again, Ray was used to backfill these embeddings. So why did we choose to use Ray data for these tasks? Well, first, it's because our workload is offline. Second, it's multi-stage. And third, it's heterogeneous. And let's break this down. First, we have an offline batch inference job. So compared to our existing solution of deploying an online server and calling it in a loop, we are able to, using a dedicated batch solution has many benefits. So for one, we're able to use zero-copy memory sharing to communicate between processes instead of having to set up a HTTP server and sending requests to it. We're also able to, instead of like having to balance between latency and throughput in an online setting, for example, by using dynamic batching, in an offline solution, we can purely optimize for throughput. We can always saturate the GPU memory. And finally, when you're sending HTTP requests, you have to handle the errors yourself. For example, if the model is auto-scaling up and there's some requests that are timing out, we have to deal with that manually, and sometimes the requests are canceled by the client, but it's still being processed on the server, so it leads to some wasted computation. On the other hand, Ray runs in the local cluster and is fault-tolerant, so even if a node fails, Ray can still recover. Because of these reasons and the fact that our existing solution was not the most optimized, we're able to achieve a 10x improvement when moving to Ray. And it's pretty easy to see why just by looking at this GPU utilization chart before and after. So the second point I want to make is that our job is multi-stage, and to see why, you can actually see this core logic in our clip pipeline. So we first read the Parquet file and then map a CPU preprocessing function to it, and then we use the GPU for clip inference, and finally we save it out to S3. Notice that we have a mix of CPU and GPU resources, hence this is heterogeneous. So let's keep this diagram in mind, and let's see how Ray is able to execute this efficiently using streaming and pipelining. So first, Ray breaks the dataset into partitions and the steps into stages. And as the execution starts, the first partition gets executed in the first stage, and after that's done, it's passed to the GPU inference stage. In the meantime, there's a free CPU for stage 1, so Ray starts executing the second partition of the dataset. So basically, the data streams through the pipeline, and all the stages are interleaved together to maximize the utilization. And this is in contrast to a framework like Spark, which essentially executes one stage after the other. Ray is a lot more granular and is able to use the resource more efficiently. So if your CPU preprocessing is particularly intensive, you can also easily add in an additional CPU node to help. And Ray will take care of bringing in the objects from the CPU node to the GPU node for the second step of batch inference. So you can actually see this in action in this timeline trace of our clip job. So I wanted to show you this because I think it's pretty neat. The way you read this is that each row is a separate worker process. And so you can see the CPU node on top and the GPU node on the bottom. We're using pretty intensive preprocessing logic, so we're bringing in an additional node. Almost all the rows you see are CPU workers, except for the third row to the bottom, which is the only GPU worker we have in the cluster. So reading from left to right, we first download the model on the GPU worker, and then we start executing, like all the CPU workers on both the CPU and the GPU node start running preprocessing tasks on the first batches of data. And after they're done, Ray will automatically aggregate the batches together and start the clip inference on those results. And the clip inference takes in a large batch size to saturate the VRAM of the GPU. So at the meantime, the CPUs start preprocessing the next batch of data. And it doesn't take a break at all in the middle. So this is the ability of pipelining to take advantage of the resources you have. So in this controlled experiment, we're able to achieve a 58% cost saving compared to our optimized online solution. Ray is also able to keep the memory usage down by throttling steps that are producing too many outputs for the next step. And we actually saw a huge improvement of this in Ray Data 2.10, in which the scheduler is able to predictably restrict the parallelism of tasks in order to avoid spilling memory into disk. So shout out to the Ray Data team. So moving on to the second use case we have, which is LLM Batch API. At Roblox, we're fully embracing the innovations in LLMs. And while we have many online use cases, we also have a huge demand for having a simple-to-use offline batch API. We use it for translation, in which we summarize content for Roblox experiences and translate user documentation in batches. And we also use it for safety. So as we mentioned, at Roblox, we take safety very seriously. We have an amazing team of thousands of moderators who are always conducting safety reviews on chat messages and assets on the platform. And when we have to change our policy, we have to essentially validate it by retraining the moderators and having them label some samples, and then comparing the results against our expectations. And if it's not good, then it's back to the drawing board, and we have to repeat this whole process again. So we can essentially speed up this inner loop by using LLMs to label the samples in batches according to the new policy. And this will streamline the policy drafting process and increase the iteration speed. We also eventually want to develop our own adaptable and policy-aware ML models for automated abuse detection. We have many other use cases, such as game jargon labeling and search query relevancy detection, and so on. So for the batch API, this is our architecture. We want to keep the online and the offline API in the same unified API. So we're putting this behind the ML gateway. And when the user makes a request, the ML gateway forwards it to the RAID backend service to create the RAID job in the user's namespace. And then KubeRay is responsible for reconciling the cluster, running the code, and writing the outputs to S3. We also have a front-end to show the user exactly what the progress is. Compared to an online endpoint, with a batch API, we're able to improve the throughput by efficiently handling large volumes of data. Sometimes we have more than 10 billion tokens in a single job, and it takes like maybe 10 to 20 hours to run. We can also reduce processing time by bundling multiple requests into the same call. Since all the requests in a batch job are consistently run in the same cluster, we're also able to ensure that related requests are processed together, taking advantage of prefix caching. We can also deliver more consistent and reliable outputs. And I just want to highlight, prefix caching is a huge factor in our throughput increase, because in the safety example, for example, we always put the same safety policy in front of every prompt. So being able to cache the prefix in the KV storage in vLLM has really helped us to speed it up. We also have better cost efficiency by having lower cost per token and being able to use the GPU instances when they're not being used. And finally, we also want to reserve the online endpoint so we can avoid overwhelming it. It's kind of like how you want to separate your OLAP and OLTP databases. So this is our API. It actually is very similar to the OpenAI batch API, but we did have to expose a lot more parameters. For example, we let users customize all the vLLM parameters, so they can like deploy their own. They can use their own models if they want. We also, behind the scenes, we also use the same logic as we did for the clipping example, but in this case, we're using vLLM as the batch inference engine. We ran into numerous challenges when developing this. First is that LLMs are quite large, and sometimes it takes a long time to download them. So sometimes up to 30 minutes, which really lowers our utilization of the nodes. And our solution was actually to use the NVMe storage as a way to cache the weights, and also use a more optimized downloader that's able to achieve a speed of 5.6 gigabytes per second on a P4DE instance. We also want to allocate the GPU instances more efficiently, and Yiqing will actually talk more about like our custom GPU scheduler to like use the spare GPU instances and also bin pack the GPU nodes. And finally, we want to have a multi-tenancy support. We want to prevent a single user from just overwhelming the entire cluster. And we do this by essentially deploying a job in the user's Kubernetes namespace, and we have a resource quota on each namespace. So now that we've established that Ray was very helpful for us, I want to pass it to Yiqing to talk about how we built a platform around it.
Hey, thanks, Steve, for talking about the use case of Ray job at Roblox. So now let me talk about the Ray job platform at Roblox. So since the launch of our Ray job platform, we have seen numerous teams within Roblox quickly adopting it to run their compute-intensive workloads. So actually, we are seeing hundreds of jobs being scheduled daily just to support a wide range of use cases at Roblox. And this is our architecture of our Ray job platform. And we built it on top of the open source KubeRay and KubeRay API server. So when we design it, we really focus on these 4 key points. So first of all, it needs to work seamlessly with the existing multi-tenancy and GPU scheduling setup. And secondly, we provide simplified API with sensible defaults, so which helps our user to safely ignore the Ray head complex configuration and really focus on what matters most to their business needs. And we also provide pre-configured compute templates to help streamline the setup process, which I will show you later in the following slides. And we also provide deep integration with Kubeflow, and this helps our user to use Ray along with the other ML stacks at Roblox. And lastly, we also automatically persist the logs and metrics using the company low-key and Prometheus, and we believe this gives the user a comprehensive observability and insights. So this is the front end of our Ray job platform. As we can see from this screenshot, for this namespace, we show all the Ray job status, creation timestamp, and the Grafana, the corresponding Grafana links and a job message. And the user can also create a new Ray job by click the Create Job button. So that prevent them from deal with the complex YAML manifests of Kubernetes. And this is our panel to create new Ray job. So as we can see from here, the user needs to specify the Ray job name, the base Docker image. They can also specify the entry point. For the compute template, they can either select the pre-configured compute templates. They can also specify their own custom compute templates. And of course, they can store the custom compute templates for future use. And this is the overall UI of the job creation panel. So now let me talk about the GPU scheduler. So we used to have some problems. So for example, the team owns specific nodes, and they need GPU type specific quotas. And secondly, the teams expect immediate GPU allocation, even though they don't use them 24/7. And we also experienced resource fragmentation, which makes the pods hard to get scheduled. And we also observed that users spend a lot of time figuring out which nodes are available. So here are our solutions. So we are migrating from allocating the specific nodes to the teams to a system where all the nodes are interchangeable. So we have a repo to manage quota as code so that the user now owns a unicorn queue instead of the specific nodes. And we also allow the user to input a range of GPU type or tiers so that we can get them the best available option, like automatically. And we also implement Unicorn for advanced queue management. We also build our custom webhook as the meta scheduler to integrate with the Unicorn queue so that we can provide the optimal queue for pods. And also, we also make sure the CPU and memory are proportional to the GPU account. So as we can see from this two diagram, the one on the top showcases the previous situation where all the teams own the specific nodes. So as we can see from the diagram, all the pods are not really scheduled efficiently to the GPU nodes. And now we move to a new system. As we can see from here, like all the GPU nodes are being used pretty efficiently, and we have more available nodes. And this is the real world screenshot of how our nodes get scheduled. As we can see from here, almost all the GPU nodes being used fully. And this slides illustrate the authentication and authorization flow for Ray job. So we follow the kubeflow architecture, and we support both OIDC for human and service account for services. So for users, the OIDC auth service communicate with the OIDC provider to verify its identity. And for service, the service account name is being added to the request header. So, once after this, the request being passed to the backend, which handles the authorization using the Kubernetes RBAC resources. So basically, the backend checked the permission of the job to check whether it has permission to create a Ray job or not. And throughout this process, the Kubernetes RBAC resources managed permissions and checked to ensure a secure access to resources. And this is our notification client. So as we can see from here, we implement our own notification client that attach to the Kubernetes job submission pod. So once a job status becomes deterministic, it sends an event to the Kafka. Then the Knative notification service pull the events from Kafka, then send an email or Slack to the end user. And it will automatically scale down once there are no more events in Kafka. And we also implement our own Roblox ML SDK to support Ray job. As we can see from the code here, we support submit job, get job, list job, and delete job. And we also provide the SDK to help our developer to sync or snapshot their local working directory to the remote Ray cluster to help them easier to iterate their Ray code. And of course, we also provide the REST API for Ray jobs. And this is our future work. So first of all, right now we use the open source Kubernetes API server. We want to improve it by implementing our own API server so that we can better integration with our company system and have a flexible iteration. We also want to improve our development workflow in addition to the SDK. And after that, right now we have CI/CD integration for model serving and ML pipeline. We also want to have a CI/CD integration for Ray job. And we also want to have cost estimation before even we submit the Ray batch job. Right now, we have a really good dashboard to track the finished Ray job. And finally, we want to have a way to expose the Ray dashboard securely, because we all know that the Ray dashboard process does have write permission. So we want to make sure we handle this properly. That's it. So now we want to have some time for Q&A.
So for Q&A, please use this microphone and raise your hand.
Hi. I have a question about the UI dashboard and the notifications you talk about in the Ray cluster. Is that something part of the open source Ray, or is it something you build custom? And is it tied to a specific Ray cluster, or is it global across all Ray clusters?
So first of all, we implement that in-house. It's not part of the open source. We write a lot of front-end code to make sure it integrates well with the Kubeflow. And the same for the notification client. We also implement our own notification client. Does it answer your question?
Yeah, there was a second.
Yeah, this is global. Like, our entire platform is like, this is enabled on the whole platform. Doesn't matter which cluster it is.
Thank
you. So I have another question. So thank you for the talk, by the way. So basically, do you have like a federation for Ray cluster over multiple Kubernetes clusters? And if you do, and how any kind of challenges for that?
So we have a lot of Ray clusters within the same Kubernetes cluster for each namespace. That's our setup.
Okay, so there's no like kind of federation across the different Kubernetes clusters.
So we actually have a lot of different environments, and all those environments are isolated.
Oh, got it. So now how about like heterogeneous Ray clusters? For example, workers with different specs. Do you have support for that?
Yes, we do. We can support, for example, like we actually support it in many different ways. So for example, the user can use the SDK to specify what kind of the resource they need. They can also use the front end, like job creation panel, to create their own compute template. And the compute template is the namespace scope, so they can really store it for future use. And of course, they can, for the really mature users, they can use the CRD like directly as well. Yeah.
All right, a round of applause for Steve, Wei, and Yiqing. Thank you.